Back to this video. We'll be looking today at a few exercises covering basic integrals that you might have come across before, but based on the standard integrals that we looked at, we'll just apply them to these examples and see if we are able to solve them. So if we look at the first exercise here, we have the integral of x plus 1 divided by x, right? So immediately when you see something like this, you can clearly see that you can separate this into two integrals. What do I mean by that? Well, we can have the integral of x over x dx plus the integral of 1 over x dx, right? And this will just be equal then to the integral of 1 dx, right? Because x over x is just 1, plus the integral of 1 over x, which from our previous basic integrals, if you go back to the previous video, we showed that that is just equal to ln of x. And we'll just leave out the constant of integration for now until we finish integrating all the terms. So the integral of a constant, right, remember, the integral of a constant dx is just equal to, if you go back to your basic integrals, it's just equal to that constant multiplied by the variable, which is x. So here we have 1 multiplied by x, which is just x, plus ln of x, plus our constant of integration, c. And so that's it for that example. Looking at the second example now, we have the integral of x plus 2 divided by x plus 1, right? So if we're to manipulate this numerator, the integral of so x plus 2 is just equal to x plus 1 plus 1, right? We can all agree on that. So, and immediately we can see that we can use the same logic of the previous example, and we can separate these into two integrals. Basically, we'd have the integral of x plus 1 over x plus 1 dx plus the integral of 1 over x plus 1 dx, right? And that would give us the integral of 1 dx plus the integral of 1 over x plus 1, which once again, if you go back to the video we made on the revision of integration rules, that is just equal to, once again, ln of x plus 1, and leaving out the constant of integration for now, we'll keep going, and we find that the integral of 1 dx, just like before, is equal to x plus ln of x plus 1, and now this is plus the constant of integration. So that is, or that should be our final answer. Looking at the next example that we have here, we have the integral of x we have the integral of x to the x multiplied by e to the 3 ln x dx. Now, if we were to try to simplify this expression, e to the 3 ln x can just be rewritten as e to the ln of x cubed. Right? And if we use what we know of exponential rules, we know that e to the 3, e to the ln x cubed is just equal to x cubed, right? So we have x, integral of x multiplied by x cubed, which is just equal to the integral of x to the 4, which we can easily demonstrate is just equal to x to the 4 plus 1, which is 5, divided by 5, plus our constant of integration c. Moving on to the next example, we have the integral of 1 over cosec of x. Again, this can be, we can try to simplify this further. We know that cosec is just 1 over sine. So we have the integral of 1 over sine of x dx. And that can just be equal to the integral of sine x. And the integral of sine x, we know, is just equal to negative cos x plus the constant of integration c. The next example is equal to, there's two ways you can solve it. Right, so we know that 1 over cos squared can just be rewritten as 1 over cos all squared, right? So all under the square. So we can rewrite this as that, right? So then we know that from our trigonometric identities that 1 over cos is just sec, right? So we have the integral of sec squared here, sec squared of x. And if we go back to our standard integrals, the integral of sec squared of x is just equal to tan of x plus our constant of integration. So this one is a little bit straightforward. So that's one way to do it. Another way you could have done it is you could have changed this 1 here in the numerator to cos squared plus sine squared, because remember from the trigonometric identities, once again, cos squared plus sine squared is just equal to 1. So you can replace this 1 in the numerator with cos squared plus sine squared, and then you simplify, but you would end up having the integral of sec squared again, which will give you the final, the same final answer, tan x plus c. So moving on to the next integral, we have the integral of cot squared of x plus c. Right. So let's try to simplify this. We know that cot is equal to cos over sine. So here we have cos squared of x divided by sine squared of x plus c. Sorry, plus 1. And if we're to put these two terms to the same denominator, we have cos squared, the integral of cos squared of x plus sine squared of x, all divided by sine squared of x. And we remember that cos squared of x plus sine squared of x is just equal to 1. So we end up having 1 in the numerator divided by sine squared of x in the denominator. So, and that is just equal to the integral of 1 over sine. We know that 1 over sine is cosec, so this is just equal to the integral of cosec squared of x. And if we go back to our standard integrals, that integral is just equal to negative cot of x plus c, the cos terms, right? So moving on to the next example, we have the integral of 1 over sec plus tan, right? Let's try to simplify this again. So sec, we know that sec is just equal to 1 over sine, 1 over cosine, sorry, 1 over cosine of x, and tan is just equal to sine of x divided by cos of x. Putting this to the same denominator and simplifying, we have 1 over 1 plus sine of x divided by cos of x. And simplifying further, we get in the denominator 1 plus sine of x, and in the numerator we have cos of x. So our integral is changed to the integral of cos over 1 plus sine dx. And for this specific integral, we can use our loyal, trusted way of solving it, which is u substitution. So we could say, let's make some room. We could say, let u be equal to sine of x. Then immediately we know that our du will be equal to cos of x dx. Once again, if you don't remember integration using u substitution, try to go back to the previous videos, tackling those, and then you'll have a bunch of examples there that help you sort it out, right? So we have du is just equal to cos x dx, meaning that dx is equal to du divided by cos x, right? So we know that. Now if we apply this to our integral, we get dx being equal to du over cos, right? Oh, sorry. Keep it there. And we have that our u is sine, so we have 1 plus u. And in the numerator, the cos stays there, but it cancels with the other cos in the denominator. So now we can rewrite this as the integral of 1 over 1 plus d plus u du. Right, so our integral is fully in terms of u now. And if you go back to the basic integrals that we did when dealing with one of this form, you know that this is just equal to ln of the absolute value of 1 plus u, or rather just 1 plus u. And I'll just explain just now why we included the absolute value here, plus a constant c. Rather, sorry, it would be u, yes. But then if you substitute u with the original u substitution, you'll have the integral of ln of 1 plus sine of x, the absolute value of sine of x, rather ln of the absolute value of 1 plus sine of x plus the constant of integration c. And now we see that the reason why we included the absolute value here is, once again, sine can have both positive and negative values. And we are trying to stay away from having ever having a negative under the ln, right? So that's why we just include the absolute value there to get rid of any of those eventualities. Right, so moving on to the next question, we have, let's just make some room. We have the integral of sine cubed of x times cos of x plus sine of x times cos cubed of x. So we can clearly see here that sine x cos x is a common factor for these two terms. So we can take that out. So we can take out sine of x, and cos of x is a common factor, and then we are left with sine squared of x plus cos squared of x, right, in the bracket. And that, we know that that is equal to 1. So really what we're left with here is the integral of sine of x multiplied by cos of x dx. And that is just equal to, if we go back to our we can use, so there's two ways we can do this. We can use u substitution, or we can use our rules that we know for double angles. So if we go back to our rules of double angles, we know that sine of 2x is just equal to 2 sine times cos, and therefore if we could, when you reverse that, you get that you have sine of 2x divided by 2, right, which will just give you the same answer there. And when you integrate this, 1 over 2 is a constant, so you can take it out of that integration, and you're basically integrating sine of 2x, which we know is equal to negative cos of 2x divided by 2, divided by 2 plus our constant of integration c. And we can simplify this further to just be negative 1 over 4 cos of 2x plus c, the constant. And that should be our final answer. Then if you apply that to the next example, which is dealing with the integral of 2x plus 1 divided by x squared plus 1. Now, right away you can see that you can separate this integral into two separate integrals again, where we have the integral of 2x over x squared plus 1 as the first term, and the integral of 1 over x squared plus 1 as the second term. Now for the first part here, we have that you can clearly see that the numerator is the derivative of the denominator. And this brings us back to which row? Let me just brings us back to this, the fifth row of our integration, when we have the numerator being the derivative of the denominator, and the rule tells us that that is just equal to ln of the function in the denominator. So we know that this first integral will just be equal to ln of a function in the denominator, which is x squared plus 1. No need to include absolute values here because we have x squared plus 1 will always be positive. So that's for the first integral. For the second integral, we have 1 over x squared plus 1. Yes. So if we go back to our basic integrals, 1 over x squared plus 1. So if we look at 15 here, the integral of dx over x squared plus a squared. If we put it side by side with our integral that we have to deal with here, we can clearly see that a is just equal to 1, right? A is equal to 1 for this case. So we have 1 over 1, which is 1, multiplied by 10 inverse of x over 1, which is just 10 inverse of x, plus our constant of integration c. So this should be our final answer. Now moving on to the next example, we have the integral of cos 3x over 2 plus sine of 3x. And here we can make use of your substitution, or we can also sort of intuitively see that if you derive the denominator, so in the denominator we have 2 plus sine of 3x. If you derive the denominator, you will have that the 2 falls away because it's a constant, so the derivative of constant is 0, plus the derivative of sine 3x, which is cos 3x, right, but multiplied by 3. So the only thing that is missing in the numerator here for it to be the derivative of the denominator is the 3, right? So to take care of that, we can multiply and divide by 3. So if we multiply by 3 and divide by 3 here, in such a way that 3 can still be cancelled without affecting our function that we are integrating, then we can see that in the numerator now we have the 3 necessary for it to be the derivative of the denominator. And this 3 in the denominator can come out, right? We can take it out as 1 over 3. And then when we integrate 3 cos 3x over 2 plus sine 3x, we have that is just equal to ln, right, of the absolute value of 2 plus sine 3x plus our constant of integration c. Once again, I challenge you to attempt this problem using U substitution, right? Just sort of as a revision for what you did when you're solving integrals of using U substitution. So try to solve this using U substitution and see if you end up getting the same solution. You should. So looking at the next problem, we have the integral of e to the 3 tan x times sec squared. If we make use of U substitution here, right? If we make use of U substitution, we can say let our U be equal to tan of x. And immediately we know that if U is equal to tan of x, du, the derivative of U, is equal to sec squared of x, right? Dx. Dx. Meaning that dx is just equal to du divided by sec squared of x. Right, so we have that. If we go back to our original integral now and apply our substitution, we have that is just equal to e to the 3u, right, multiplied by sec squared multiplied by du over sec squared of x. Right, and immediately we can see that sec squared can be simplified away to be equal to now the integral of 3u e to the 3u du, right? And if we go back to the revision, the video on the revision rules that we did before, we can see that for a specific case like this, when we know that this integral would just be equal to e to the 3u divided by 3 plus our constant of integration. Now let's remember that we substituted originally u with tan of x. So if we go back to the original substitution, we get that this is equal to e to the 3 tan of x divided by 3 plus c, the constant of integration. And that is the last exercise that we'll be looking at for this revision session on integration. So you're free to go back and pause at any moment during the video before we solve the exercise and try to attempt it on your own and see if you're able to. Otherwise, you can just unpause the video and see how to solve it, and then try again and see if you are able to figure it out. Right, so thank you for watching, and I'll catch you guys in the next video. Thank you. Bye.